So before we look at the only lemma and theorem we're going to look at in section 2.4, we need to define a function. So we're going to define it kind of using this example. I've drawn a function up here, and notice it is an increasing function. It's never decreasing, so I like to say it's non-decreasing, but it is an increasing definition based upon the definition we wrote on the board. The domain of the function looks like it is from 0 to 10. Now, what's the image of that function? Another way of writing that is, what is f of the domain? What set would that give us? What are all the heights that value, the heights or values that function takes on when you plug in all the numbers in the domain? Anybody want to give that a shot?
1 to 4 inclusively, and then 7 to 9, but not including 7.
Yeah, it would start at 0, right?
Oh, 0.
It start at 0. So the heights the function takes on include everything from 0 to 4, inclusive, union with whatever this is. Yeah, 7 and 9, not including the 7. Okay, so that's the image, all the possible values the function can take on, the heights of the function. So before we start talking about continuity of monotone functions, I want to define these two functions, u of x and L of x. U of x is going to be the infimum of all of the f of t's where t is bigger than x, right? X is less than t. And L of x is going to be the subprimum. L of x will be the subprimum of all of the heights of the function f of t, where t is all the numbers less than, strictly less than x. All right, so let's see. Before we just guess what these numbers are, let's maybe write it down. That would be the infimum of, so my x is the number 4 in this case, and we're using this function. So u of capital 4 is going to be, the t is just a dummy variable. So x is 4. I think I'm going to write it like t greater than 4. I kind of switched it around there. Instead of 4 less than t, I wrote t greater than 4. And looks like I'm not staying level here, but L of 4 would be the supremum of f of t, where x is a 4, where t is less than 4. Sorry, these things just didn't line up very well. All right, anybody want to take a stab at what the values would be? It's just going to be a number in each case. So we're looking, for this case, we're looking for u of 4 and L of 4. So here is x equal to 4. Think of that vertical line if you want to. And if x is, well, if t is bigger than 4, you're talking about all this. And if t is less than 4, you're talking about all this. So maybe we'll do the L first. It's the supremum of all of the heights of the function where t is less than 4. So from here to the left, what is the supremum that all of the heights of that function take on? Let's remember what the supremum is, the smallest, least upper bound. Well, what are the heights of the function that this function takes? The heights or the values that this function takes when t is less than 4, it would be all of these heights. T, all these numbers, all of these heights. Well, the supremum of that is going to be the height of 2. You agree with that? So just look at this. What's the greatest value that the function takes? Now that doesn't define the supremum, but in this case it does. The highest possible value it takes is the number 2. So L of 4 is just equal to 2. Well, u of 4 considers only the numbers that are greater than 4, to the right of 4. And we're looking for the infimum of all of the heights of the function from here on. The infimum will be lower bound, the greatest lower bound. So the lowest height that it takes is what? 2. And that turns out that we'll see in a minute, that's a good sign. We'll see in a few minutes that that means that the function is continuous at that point. Let's do the same thing with the number 6. Notice it's going to be a little bit different this time. So u of 6 is the infimum of f of t, where t is greater than 6. And L of 6 is going to be the supremum of f of t, where t is less than 6. So we're looking at the left and the right of 6. So if we look to the left of it, for all values less than 6, what is the supremum of all of the f of t's if t is less than 6? What is that? 4. Yeah. What is the, if you look at the heights of all the functions, the heights of the function or value of the function as I'm moving this way, it's 0 here, it's a height of 2 here, and the height is 4. So it's the biggest height that it takes on there. So that's going to be a, let's see, we did the t less than 6. This is going to be a 4. We took the supremum of the number of the heights to the left, and now we're going to take the infimum from all of the points to the right of 6. So to the right of 6, what is the infimum of all of the heights of that function or values of the function when t is greater than 6? Yeah, it's going to be this one, because we're not including the case where it's equal to 6, which would be a 4. So really, we're only looking at this. And again, it's not the absolute lowest value. It may not take that value 7, but you can see that the limit, or the infimum of all of these heights from 7 to 9, it's an open interval here, would be 7. Any questions about just how we computed these numbers, 2, 2, and then 7 and 4?
So how do we get
7? How did we get 7 and 4? Let's look at 7. We did 4 first. Let's look at that. This means the height of the function f of t when t is less than 6. So all of the heights that it takes on go from 0 up to 4. Can you see as we go this way? The biggest height possible is when we get right here. Although even if it were filled in here and open here, it would still be the same thing, because we're taking the supremum of all of the heights from, if we took the supremum of all the heights from 0 to 4, it doesn't matter whether it's an open included or not.
So why wouldn't we take 7 then?
We don't take,
From the
or
left?
on the left, why did we get 7? Because
Like we got 4, but you're saying it doesn't matter if it's included or not. So why is it 4 instead of 7 for the supreme?
well, I mean, this part doesn't even exist if you're talking about t being less than 6, and even strictly less than 6. We're only talking about on the x-axis, the open interval, and the numbers going that way. Okay, so I mean, one way you can think of it, we're talking about monotone functions. In this case, an increasing function. Just take your fingers, and go out and look at what the heights do when you go from the left and when you go to the right. Think of the limit. Where are you ending up? Well, here I'm ending up at 4. Here I'm ending up at 7, a different number. Does that help? I mean, hopefully it will. And you're gonna have a homework problem that deals a little bit with this. So hopefully you have a question? Are we okay?
So supreme is pretty much from right to left?
Well, the supremum of a set, maybe I should have reviewed that. The supremum of the set is the least upper bound of a set. Okay? The least upper bound. So, if you're looking at all of the heights that the values of the heights of this function, or the value of the function, you can see that's 0, it comes up to 2 here, and it gets up to a height of 4 here. So the only heights it takes on are from 0 to 4. The supremum of that is the number 4. If you're looking at to the right of 6, the values it takes on are from 7, not including 7, up to 9. The infimum of this set is the number 7, the greatest lower bound. Okay? Okay, and we'll use these in the lemma and the theorem to follow.